Okay, so this is the higher paper question 6. Following the Chernobyl nuclear reactor accident in 1986, RIMNet, the Radiation Incident Monitoring Network, was installed across the UK to monitor the consequences for the UK of nuclear incidents abroad. GM tubes, now a GM tube is a Geiger Muller. Okay, so it's the name of the people who invented it basically. So a Geiger Muller tube are used to measure background levels of radiation. The permanent monitoring stations in Wales are located in the places shown on the map below. Okay, so Rhyl Valley and so on. So the first question says, suggest why there is more than one monitoring station located in Wales. So I put it here to improve the quality of the data, but any reference to collecting more data, spread of data, covering the whole country, I would get you the mark. Okay, so we're making sure that there are a number of stations north to south and reasonably well east to west. Okay, so it's to improve the quality of that data. Now, the next question says the background count at one of the monitoring stations is 24 counts per minute. Explain how, using a stopwatch and a GM tube connected to a counter, an accurate value for the background count is determined. Okay, so just to remind ourselves, whilst they're not called GM tubes on here, basically this is the part of your knowledge organizer we need to be concerned with. So we've got a source here, which in the case of the ones in these monitoring stations is just the environment, and then we've got a detector which is mounted to a counter. And these counters, you know that radiation is hitting the detector because the counter clicks. Okay, there's a visible click, but also an electrical sort of signal is generated. So if you can count those for 1 minute, how many clicks that you hear, then you get an idea of how much radiation is available. So if it's at the rate of 24 clicks per minute, that's perfectly countable by a human. In a really radioactive environment, that would have to be done electronically because the clicks are so fast that you couldn't possibly count them. Okay, so 350 counts per minute would be quite difficult to count if you were doing that as an experiment. Okay, whereas 20 and 1 would be far more possible. Okay, so this is the Geiger Muller tube. So if we go back to the question, so it says the number of clicks measured on the counter in a minute is recorded. On numerous occasions, a mean value can be calculated. Okay, so you need to do readings over a period of time. Okay, just to make sure that you are getting an accurate value for the background count, because there may be certain things that vary in the short term that affect your value, but you would want to get an average over an extended period of time. Okay. Now, this question, a little bit more sort of accessible possibly. Two radioisotopes released from the Chernobyl accident were iodine-131, okay, and cesium-137. The decay curve for a sample of iodine-131 is shown in the graph below. So this is your typical half-life graph, okay. So we've got the y-axis in this case is activity. Okay, it doesn't matter what the y-axis is, to be fair, on these types of graph. It could be the mass of one of the isotopes. So the shape of the graph doesn't change, and we can see that it's decreasing rapidly, but then it slows down in its decrease. So it tells us, first of all, you need to state the meaning of half-life. Okay, now need to be absolutely clear on this. The half-life is the time needed for the radioactivity to halve. Okay, so on this particular graph, we've got a measure of radioactivity. So it's the time period. So half-life is a time period needed for the radioactivity to halve. Okay, so the next question, well, one of the next questions will deal with how we actually work that out. So use information on the graph to determine the half-life of iodine-131. So you can see that I've already got the answer there, but we've got to go through how I came by that. So in order to calculate the half-life on any graph, you need to first of all identify the maximum value of activity or of mass, whatever the maximum value is on the graph, find out what it is. Then you need to half that value, okay? So in this case, we've got 1600, half of 1600 is 800, okay? So I would advise that you draw a nice bold line on your graph to show the examiner you know what you're doing. And then from where it touches the half-life graph, you drop down a vertical that then points to the x-axis, and we can see there that this is 2 days short of 10, so obviously that's 8 days. So the half-life of this particular isotope is 8 days. Okay, so we're doing that. Now, this next question I felt was quite difficult, quite laborious, but we'll see how we get on. So it says a sample of cesium-137 with an activity of 1.5 becquerels was obtained near Chernobyl. Calculate the time taken for this sample to reach a safe limit of 1/512 of its original activity. The half-life of cesium-137 is 30.2 years. Okay, now the hard thing about this is you've got to go through this process here of working out how many half-lives it is to get from the full dose to 1/512 or 512th. Okay, so it goes from full dose to half in 1 half-life, and then from half to a quarter in 2, from a quarter to an eighth in 3, and so on and so on and so on and so on. If we count these half-lives, there should be 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9 half-lives to get to 512, because in each of these we half the previous value. Okay, so 9 half-lives, but each one of those half-lives is 30.2 years. So we need to multiply 9 by 30.2, and that gives us 271.8 years. Okay, so it's quite a long time for it to drop down to that level. It may be safe before 1/512, but we can see that the half-life of cesium, being 30 years, is a lot longer than the half-life of the iodine, which is 8 days. Okay, so the final question takes that into account. Explain why in 2021, 35 years after the nuclear accident, scientists were concerned about cesium-137 contamination in the Chernobyl area, but not iodine-131. Okay, so basically the half-life of iodine is much shorter than that of cesium-137. Therefore, the radiation due to iodine will have decreased rapidly, or will have gone down a great deal, whereas the radiation due to the cesium is still going to be reasonably high, because the half-life of cesium is 30 years, so it's not a great deal longer than the 35 years since the accident. So there will still be a great deal of radiation due to cesium-37 in the area, whereas radiation due to iodine-131 will be significantly less. Okay.